Welcome to PHONEXIA's presentation, which will introduce our voice biometrics technologies integrated into the TENSOR platform. The main challenge that our technologies solve is identifying a speaker in audio recordings. Our speaker identification technology can identify a speaker's voice from only 3 seconds of net speech, regardless of the language and words spoken. PHONEXIA voice biometrics technologies can also label multiple speakers in mono audio recordings based on voice and even help filter large amounts of audio based on gender. The primary technology PHONEXIA provides is speaker identification, which helps answer the question of whose voice is in the audio recording. It supports one-to-one voice verification and also one-to-many and many-to-many speaker identification. There are also two supportive technologies, speaker diarization and gender identification, to make the work with audio more seamless. Speaker diarization can separate speakers in a mono audio recording based on their voice, and gender identification can help filter audio faster based on whether a speaker is male or female. All these three voice biometrics technologies are language, text, accent, and channel independent. Voice biometric speaker identification consists of two steps. Firstly, a speaker model, known as a voiceprint, is extracted from an audio recording. Such voiceprint is a complex mathematical model of a person's voice that cannot be reverse engineered into the person's original voice, which makes it highly secure for data handling. Secondly, the extracted voiceprint is compared with other already extracted voiceprints in a database, resulting in log likelihood ratio scores. Out of these two steps, the most time-consuming operation is the voice extraction. The voiceprint comparison itself, however, takes only a fraction of the time. Millions of voiceprint comparisons can be performed in a few seconds. For the TENSOR project specifically, PHONEXIA has simplified its voice biometrics technologies so that they are very easy to integrate via a gRPC protocol. We have also improved the processing performance of these technologies by enabling GPU processing. We have also greatly improved the accuracy of speaker diarization technology. The input for our technologies is an audio recording. To identify a speaker in audio, it is necessary to receive an audio recording with at least 3 seconds of net speech. For speaker identification and gender identification, the results are in the form of a log likelihood ratio score. For speaker diarization, the results are provided in the form of timestamps, labeling the exact position of individual speakers in the mono audio recording. Our voice biometrics technologies will be applied in use case 1, which aims to assist the police in identifying and verifying criminals involved in a bank robbery. Specifically, it will be used as a supportive technology when the user decides to proceed with voice analysis because the face analysis result is of low confidence. The audio recording from the CCTV footage is sent to the voice biometrics module for further processing, returning a list of possible voiceprint matches based on a score value exceeding a given threshold. Let's demonstrate how these voice biometrics technologies can be used to help solve this use case. For the TENSOR project, PHONEXIA provides voice biometrics technologies as microservices, which means they don't have their own graphical user interface. To showcase their functionality, we will use a demonstration tool that can run these technologies and display the results. Once again, this is not the graphical user interface in TENSOR. It is purely a demonstration tool to showcase the functionality of these voice biometrics technologies provided as microservices. As we receive a mono audio recording from the CCTV footage, in which multiple speakers are speaking, we first want to split these speakers into separate audio files. We will use the speaker diarization technology for this. Here, we can see the results. The speaker diarization technology has labeled 4 different speakers in the audio recording that we can now split into 4 separate audio files. As we have split audio recordings per individual speaker and know the suspect is a male, we now want to filter only those audio recordings that contain a male voice. We will use the gender identification technology for this. As we can see, the technology has identified 3 female voices and 1 male voice. We can now process this audio file with the speaker identification technology to compare the person's voice with other voiceprints of known suspects in a voiceprint database. First, we will extract the person's voiceprint from the audio recording using the speaker identification extractor microservice. Once done, we compare the extracted voiceprint with the voiceprints of other known suspects using the speaker identification comparator microservice. As a result, we receive a log likelihood ratio of score per each voiceprint comparison. The higher the score, the more confident the system is that the voiceprint belongs to that specific person. In this case, we can see that the speaker identification technology is very confident that the voiceprint belongs to suspect number 1.